Okay, so why do we do this area? So let's assume now that we have that this is like this is velocity. Um, and it's I know that this is my velocity and this is my time. Now, assume I want to know the distance traveled. So if velocity is constant, my distance traveled is going to be my velocity, my change in velocity times the change in time. And and then I, could find that distance. But here it's not constant. So what we can do is we can say, well, let's pretend it's constant. So let's just take a random interval here. Say we're trying to go from 0 to 5. So let's start here actually. So let's just go here and say, okay, let's just pretend it's constant on a little interval. It's almost constant. So the formula that I use, I'm going to use my formula, my constant formula on this interval. So my distance here, my width is, my distance traveled is delta t, and my height is velocity, at 1. I'm sorry, at 0. So I plug in 0 and get this velocity here and just pretend it's constant here. Now you can see this is actually also the width of a rectangle times the height of the rectangle, which is giving me the area of this rectangle. And then if I come over a little tiny distance and I do it again here, I pretend it's constant on this little tiny interval, and I can do the same thing. On this interval, it'll be delta t times v of um, that next point. Let's just say it's 0.5. And then we can add those up and get the total distance traveled. Now, as we saw, that's not exact. There's going to be some error, although it looks very exact on my drawing, but there's going to be some error. You can see it more right here. So, what we can do is we can take the smaller rectangles, smaller intervals will get us even closer to the um, the exact area or the exact distance traveled, which is the same thing. Because as I said, doing the distance of doing this formula on each little interval is the same as finding the area of that rectangle. So let me write that. So if we can take these little rectangles to be super small or infinitely many, then we can do the limit as the number of rectangles, which is n, goes to infinity of, my formula that I'm about to give you. So this is kind of what the definite integral, this is what the definite integral is going to be. So let's just go back to these Riemann sums. Let's go back to what we had earlier. We had x squared plus 1. And we went from 0 to, let's just go from 0 to 6. Except this time, I'm going to say I'm going to break my interval into, or actually, let's just go from A to B. So let's go from any point A to any point B. Okay, and now I'm going to break my rectangle into an arbitrary number. I'm just going to have n rectangles. So my width is going to be my starting point minus my ending point over n. And I'm going to have n rectangles. All right, and then now whenever if I do the right Riemann sum, or let's start with the left Riemann sum, I'm going to come over here, plug in, go across, draw that rectangle. So now if I'm looking for the area is going to be my, f of a times my width, which is delta x, plus, and then I'm going to come over to the next point here to draw my next rectangle. But we can see if this is delta x, then this point right here is just a plus delta x. And then times delta x plus. And then likewise, this point will just be a plus 2 delta x. And we can keep doing that until we get to this one right before b, which will be on the n minus 1. And you can see we have like this pattern. We plug in a times delta x plus, plug in a plus delta x times delta x plus. And you can see we keep doing this, right? So we have like just kind of a fancy way of writing that in math. We write that as a summation. The sum is the plus. Do something and then add. Do something and then add. Do something and then add. That's what this sum means. And this something is going to go from 0. You see, this is the same as a plus 0 delta x. This is a plus 1 delta x, and then a plus 2 delta x, and then it would be a plus 3 delta x. So you see that we keep this number right here keeps going up by 1. So we have a k delta x times delta x. That's that width. And we're going to stop it here at n minus 1. So you can see that this just means plug in a 0 and you have f of a times delta x. Then add, plug in a 1, you have f of a plus delta x times delta x. Plus, plug in a 2, so you just iterate up. And then we can take the limit as the number of rectangles goes to infinity, and that would give us our definite integral. Likewise with the right endpoints, you can do it with right endpoints. It's the same thing. This is going to start at 1 and end at n. Remember, it started 1 over to the right and ended on the right endpoint, which would be this, which is also going to be b. Um, and that would be my right Riemann sum. And also the definite integral. So we can see that the definite integral gives us the area under the curve, because that's what we've been doing this whole time. And we can see these formulas are used. Now, for the exam, I only expect you to do approximate area. This is just the idea behind the definite integral. For the exam, you just need to understand that if you have a graph that is nice and gives you a nice geometrical shape, like let's just say this is 3 and this is 3, then if you want to find the integral from 0 to 3 of f of x dx, you only need to find this area under this, in this triangle, which is 1/2 base times height. So the base is 3 and the height is 3. And so we get 9/2. That's also just a concept you need to understand. All right. Well, let me know if you have any questions.